Okay, next section, 3.2, is all about derivatives and graphing. Okay, the derivatives tell us what its original function is doing. So if you know what f prime, the sign of f prime, then you know what you partially know what f is doing. If you know the second derivative of f, so f double prime, you know what f is doing, or at least in some regards you know what it's doing. In this case, it says right here, the first derivative of a function can be used to determine which intervals it's increasing or decreasing. Once these intervals are determined, possible extrema can also be found. So extrema means extreme values. So that's thinking like stuff like mins and maxes. Okay, you can find minimum values and maximum values based on that first derivative. Concavity involves the second derivative. Okay, we kind of just talked about that with a linear approximation. It tells us how it bends, okay? And then once those are determined, you can find possible inflection points using the second derivative as well. If there's inflection points there, it can find it. If there's no inflection points, it can also find that as well. But inflection points is when the concavity changes. So say I had a graph where it's like concave down, and then all of a sudden it's concave up. Okay, you can see there's some point here where it changes from bending down to bending up. Okay, we're going to go over that in more detail, just kind of preloading your brain here. So mean value theorem is basically tying together the concept of average rate of change and relating it to the instantaneous rate of change. So it's the good old-fashioned slope with the new derivative. So the slope and equal to the derivative, and kind of ties those two things together. It'll make more sense once we get to that section. Again, just preloading your brain with this slide right here. Let's start with 3, 2, 1, increasing, decreasing intervals, as well as extrema. Again, extrema, mins and maxes. Standards. Existence theorems allow us to draw conclusions about a function's behavior and interval without precisely locating that behavior. Okay, so again, the derivative tells us something about what the function is doing, the function's behavior. That's what it says right here. A function's derivative can be used to understand some behaviors of functions. That's what we're going to be doing, is analyzing these behaviors, namely increasing and decreasing. What you should be able to do, first one, justify conclusions applying the extreme value theorem. Extreme value theorem just basically means there is an extreme value if there's a function on a closed interval, which just means there's a min or a max if something is on a closed interval. We're going to talk about that in a little bit. And then next, just justify conclusions about the behavior of a function based on the behavior of its derivative. So if you know what its derivative is doing, you know what the behavior of the function is doing in some regard. In this case, whether it's increasing or decreasing. Okay, things you need to know. If a function is continuous on an open interval, extreme value theorem guarantees that the function has at least one minimum value and at least one maximum value on that open interval. Okay, there has to be a min or max somewhere in there based on extreme value theorem. The first derivative can provide information about the function in its graph, including where it's increasing or decreasing. So the main thing you need to burn in your memory is the first derivative tells us where a function is increasing or decreasing, if it is at all. The first derivative can also be used to determine the location of extrema. In this case, this should say relative extrema. That's embarrassing. Relative extrema. And that's just basically relative mins and maxes. So basically hills and valleys. We're going to talk about that in more detail. It can also help you find critical points that can help you find other extrema, like called absolute extrema or global extrema. Okay, again, we're going to go over that in a little bit more detail. Again, just preloading your brain. Here is the golden ticket here of what this the first derivative tells us. If the first derivative is positive, so wherever the first derivative is positive, that means f is increasing. Okay, the derivative, I want you to notice that the derivative tells us where f is increasing. Okay, I kind of want you to see this picture right here. You'll notice that right here, going left to right, this function is increasing here, and it's increasing here. I'm going to color code this green. Okay, you'll notice where it's increasing there, the derivative is positive. So right here, positive derivative and positive derivative. Okay, it's above the x-axis. I'm going to erase this a little bit because it's negative down there. There we go. Okay, but you'll notice it's positive everywhere else. It's positive wherever f is positive. So I color-coded the derivative to be blue here, and then the actual function to be red. And you can see where red is increasing from left to right, it's going up, like you're going up a hill. The derivative is positive. Okay, now let me change colors here so we can explain another one. Where the derivative is negative, f is decreasing. If you notice this part of the blue down here, the derivative is negative, okay? Because it's those blue dots, that's what represents the derivative. And if you notice, f is actually decreasing on that interval. The function, the red function there, it's highlighted blue now, is going down where the dotted function is negative. Okay, wherever the first derivative is 0, then f is not, it's not increasing or decreasing. It's just kind of at a standstill. Where that happens, okay, where it says where the derivative is equal to 0. Well, the derivative is equal to 0 here and here. So that dotted graph right there, that's where the derivative is equal to 0. You'll notice that the original function, it's at a hill and a valley. Okay, it's either increasing or decreasing because it's either at the top of a hill or the bottom of a valley. Okay, so I try to color code all that. I should highlight it here too. So that's that, and that. Where the derivative, so that dotted line, or that dashed line, is equal to 0. It's equal to 0 right there and right there. You can see the original function, the f graph right here, it maxes out or it mins out there relative to what the points are around it. So it's a relative max and a relative min. Okay. Now, just to kind of solidify this understanding of extrema a little bit more, I'm going to tell you all about all the flavors of extrema that you can have. Okay, so it says types of extrema. Again, extrema just means extreme values. I'm going to write that in real quick. Let's draw up this graph a little bit here. Now, if you notice with this, a relative extrema, like a relative max in this case, happens at a hilltop. Okay, that's what's going on right there at this hilltop right here. Okay, if it's the bottom of a valley, like right here, it's a relative min. Okay, this one right here is a relative min and absolute min. Absolute just means it's absolutely the lowest or absolutely the highest. So if you notice this one right up here, absolute max, it's happening at this spot right here. That is because there is no y value that's bigger than that. It doesn't go any higher than that absolute max. Okay, where down here it doesn't get any lower than this, so that's the absolute max, or absolute min. It can be the absolute and relative min, like this example shows right here. Okay, so you have to understand the absolutes do not have to happen at a hill or a valley. It can, like this example right here, but it also can happen at the endpoints, which we're going to talk about in more detail in a little bit. Okay, so relative, I'm going to write this down, relative extrema, if it's a min, it's happening at a valley. Okay, obviously valley is not a math term, but it paints the picture. It's the bottom part. And then the max happens at a hill, the hilltop. I'm just going to write a hill in here, okay, like this part right here. Okay, absolutes just mean the absolute biggest y possible and the absolute smallest y possible for the max and min, respectively. Make sure you understand that, again, absolutes can happen at the endpoints, or it can still happen at where relative extrema happen as well. Now it says right here, relative extrema, and it says right here, relative extrema can happen where points of the derivative are equal to 0 or they're undefined. Okay, that is important to understand. All relative extrema actually happen at points where the derivative is either equal to 0 or undefined. And you can kind of see that given this graph right here. You can see right here the derivative there is 0. The derivative here, because it's a sharp turn, is undefined. And then right here the derivative there is 0 as well. So that's basically relative extrema happen where the derivative is equal to 0 or undefined. Wherever the derivative is equal to 0 or undefined, that's called a critical point. Okay, again, we're going to go over that in more detail when we actually solve the problems, but just make sure you understand critical points are the x values in which, or I shouldn't say the x values, it occurs where the derivative is equal to 0 or undefined. A lot of times you do find the x values for them, though. All right, let's go further down the rabbit hole here. Okay, relative extrema. Okay, wherever the derivative changes, so right here, the derivative, wherever it changes from positive to negative, and again, remember, the derivative being positive to negative, that means that the f went from increasing to decreasing. Wherever that happens, that's called a relative maximum. Okay, so you can kind of imagine a function that's going, it's increasing and then it's decreasing. Okay, so this one's increasing here and then it's decreasing here. Whenever that happens, it makes a hill because it went up and then it went down. When that happens, that's a relative max. Okay, you can kind of see that right here. There's a relative max right here. The derivative is positive here in the blue and then it's negative here. So where it switches, that's where that relative max is happening. And the exact opposite is true if it's the derivative changing from negative to positive. So right here, derivative changes from negative to positive. If it's changing negative to positive, that means f is going from decreasing to increasing. So f is decreasing, then increasing. It can even be a sharp turn, decreasing to increasing. You'll notice it still forms that relative min. Okay, when in doubt, you can always graph it out, but main thing I do want you to be able to translate is when the derivative is negative, that means that f is decreasing. Okay, when the derivative is positive, that means f is increasing. You have to know that. I just also went over it right here. Okay, you need to make sure you memorize that. Okay, it makes kind of sense though. If the derivative is positive, that means the rate of change is positive. If the rate of change is positive, that means f should be increasing. So if you think about, like, you have a salary. If the rate of change of your salary is positive, you have a positive change on your salary, that means your salary is going up because you have a positive rate of change. Obviously, the opposite is true if it's negative. So that's basically the relative extrema. Okay, you can see the example here for relative min. So right here, it's a relative min because it happens at a valley right here, and you can notice its derivative changes from negative to positive, which again, that's what it says in that second paragraph right there. Critical numbers, I already said, this is where the derivative is equal to 0 or undefined. That's what it basically says right here. Critical numbers are the x values in which the derivative is equal to 0 or undefined, and it also has to exist. If there's no point there, then there is no critical number, and it's just impossible. Okay, so you'll notice that right here, there's a critical point there, and there's a critical point there because the slope here is 0, the slope here is undefined. Relative extrema and critical numbers. Okay, this is important to understand. All relative extrema occur at critical numbers, but not all critical numbers have relative extrema. So it works one way but not the other. If there's a relative extrema, there's a critical number. But sometimes there's critical numbers, like for example right here, the derivative is 0. But clearly there's no hill or valley. Okay, so this one here is a critical number, but not relative extrema. Okay, this one right here, there's a critical number because the derivative is undefined there. There is no derivative there. You can see there's no derivative. But the derivative is undefined there. Okay, so there's a critical number, but not any relative extrema. Okay, so again, just because you find a critical number does not mean there is a relative extrema. You have to check. I'm going to talk about that again when we do example problems, but it is important to understand that all relative extrema have critical numbers because you can't make a hill or a valley without it. But sometimes critical numbers end up being false positives, and there's not actually any extrema there. So make sure you check. And again, it'll make more sense when we do examples. 3, 2, 1, endpoints and absolute extrema. Okay, absolute extrema can either happen at relative extrema, okay, we kind of talked about that before, or it can happen at the endpoints. Okay, you have to make sure you always check the endpoints, and this will make more sense when we do the examples, but I just want to kind of show you. This right here is an absolute max and relative max because it happens at a hill, and it's also the highest y. It doesn't go any higher than that. Okay, there is no, sometimes this happens, there is no absolute min, because this one goes down, but there's a hole there, and you're never actually reaching that spot. So you're getting infinitesimally closer to that spot, but there is no absolute min. Sometimes there is no absolute extrema. That is important to understand. This point right here, though, is a relative min. This endpoint is meaningless. Okay, let's do some examples. This is a lot, I understand that, but just make sure you can always rewind, rewatch, fast forward, whatever you need to do to make sure you understand this. Ask questions in real life. That would be great. But anyway, here's 3, 2, 1. Example problem number 1. Let f be a function defined as this right here on this interval. On which of the following open intervals is this increasing? We're going to assume this is a no calculator problem because if I wanted, I could just graph this and figure out where it's increasing. But I'm going to try to do this without a calculator. Make sure you pay attention. Okay, first thing you need to understand is if it's asking for where it's increasing, that means a light bulb should be going off in your head. Oh, the first derivative tells me where something is increasing or decreasing. So I need to find that first derivative. All the stuff from unit 2 you still are going to need. So we need to find the derivative of this thing right here. So f prime g, so that's cosine x, that's f prime, times g, plus g prime f. So that is my first derivative. Now we need to figure out where it's increasing or decreasing. So the easiest way to do that is to actually figure out where it's doing neither, where it's in between increasing or decreasing. So what that means is we're going to figure out where it's equal to 0 or where it's equal to undefined. All right, this one we kind of looked out that there is no undefined because you're not dividing by 0. And one of the main things you got to see when you're dividing by 0, that's where it's going to be undefined, but this one doesn't have any division by 0, so we don't need to worry about it, but we will later. All right, so I'm going to factor out the e to the negative x, and you're going to get cosine x minus sine x is equal to 0. Okay, it is important to understand that this part right here can never be equal to 0. Okay, if you graph that, there's a horizontal asymptote at y equals 0, but it's never actually equal to 0. So for all intents and purposes, you can just kind of ignore that e to the negative x. If you wanted to, you can multiply both sides by e to the x and it's gone, but we're just going to kind of ignore it here. We are going to try to figure out where cosine x minus sine x is equal to 0 on this interval. That is important to understand. It has to be on that interval. All right, to solve this, we're going to need some trig. I'm going to add sine x to both sides. So now we need to figure out where is cosine x equal to sine x. Well, hopefully you have the unit circle memorized, because it is a prereq in this class that you have to have the unit circle memorized. And you would know that it's x equals pi over 4 and 5 pi over 4. But 5 pi over 4 is actually outside of the interval, so we don't actually need to worry about 5 pi over 4, so I'm going to erase that, and we just need the pi over 4. So we know that that's where the derivative is equal to 0. I'm going to get rid of all the ones that don't have pi over 4 in it, because it's definitely not going to be the answer. Okay, so it's between C and D right now. But we need to figure out which interval is it. So what we're going to do is make what I call a critical number line. And the critical number line is going to go from negative pi over 2 all the way to pi over 2. Okay, because that's the interval that we're looking at. And I'm going to put the critical number on the critical number line. That's why I call it a critical number line. Okay, now what we're going to do is we need to test the intervals and figure out what is going on. Let me write it down right here. What is the derivative doing here in this interval and here in this interval? Because if we know what the derivative is doing, what sign of the derivative, it's positive or negative, then we know what f is doing, whether it's increasing or decreasing. Okay, so I'm going to put a little barrier up here so it's kind of neater. Okay, now we need to figure out some value between negative pi over 2 and pi over 4, and then we're going to put that into the derivative, and then we're going to figure out the sign. Once we know the sign of that, if it's positive or negative, then we actually know what f is doing. Okay, so the best value that I can think of between negative pi over 2 and pi over 4 is 0. So I'm going to plug 0 into the derivative, and I'm going to use the factored part of the derivative because it's just a little bit easier to use. So I'm going to put 0 into that. So it's going to be e to the 0 times cosine of 0 minus 0, because sine of 0 is 0. Long story short, that's going to be positive. So I'm going to put a positive here. The derivative is positive in that interval. Well, if the derivative is positive, that means f is increasing, which is what we're looking for. Okay, now we're going to test the other interval. We need to figure out a value between these two right here, between pi over 4 and pi over 2. And the best value to do that for is probably pi over 3. Okay, well, sine of pi over 3 is bigger than cosine of pi over 3. So that means this value is going to be bigger than this value when we plug in pi over 3. Since the sine is bigger, then it's going to be negative. This value is always positive, so we don't really need to worry about it. So long story short, this is going to be negative. Now, if the derivative is negative, that means the original function is decreasing. So the answer should be from pi over 2 to pi over 4, because this whole interval right here is increasing. And that's what we're looking for. So the answer for that one should be D. Okay. Now, if you notice, it is an open interval. It's not brackets, because you can't actually increase at a point. So you're always going to have parentheses there. Just make sure you're aware of that. And make sure you know how to write interval notation, because sometimes it's not multiple choice, and you need to be able to write down the interval notation for the answer. So anyway, D is your answer for that one. All right, so this next example, it says let f be the function with the derivative given right here. Which of the following statements is true? Okay, this is actually a calculator problem, so in order to help us solve this one, I'm actually going to graph the derivative to kind of figure out which of the following is true, whether there's, no relative minimum, one relative minimum, or two, and all the other stuff that it says right here. And we're just going to base it off of what the graph is telling us, and we're going to use the fact that the relative mins and maxes can be found using all of this information that we went over previously. Okay, so if it's a relative max, that means the derivative should change from positive to negative, and if it's a relative min, it should change from negative to positive. So we're just going to basically be counting when the derivative is changing signs from positive to negative or negative to positive. But to do that, we got to use that graph. So let's go to the graph really quick to try to figure out what's going on here. All right, here is the graph of that derivative right here, and you can see that right there, there's a critical number there because the derivative is equal to 0 at x equals -1, and the derivative is equal to 0 at x is equal to 2. However, there is no sign change on this x is equal to -1. You can see it just, we zoom in right here, you can see it just grazes that x-axis and then it goes back down. It never actually changes from negative to positive. It just stays negative the whole time, except for at -1 it's just 0. So that's actually neither. It's neither a relative min nor a relative max, because again, it has to change from, the derivative has to change signs from positive to negative or negative to positive. This one changes from negative to 0 to negative again. It does not actually change signs, so that's neither. Okay, now if we go over here, however, at x equals 2, the derivative clearly goes from a negative, because it's underneath the x-axis, and then it goes into a positive there. So if it goes from negative to positive, that's a relative min, so at x equals 2, it's a relative min. So if we go back to our answer choices, there is a relative min, so A is automatically going to be out of contention, and D is going to be out of contention. So let's see here. Let me erase this here just to make it a little neater. Okay. Now there was no relative maximum, so the answer for this one would be B. This one, it says there's one relative max, which there isn't, so the answer for this one is B. If you notice, you had to use a calculator for that because you don't actually know what this graph is really doing off the top of your head. It is a calculator problem because of that reason. You have to look at the graph, try to figure out what's going on from that. Okay, another way you can do this is to make a critical number line, just like we did before. Okay, in this case, it goes, to negative infinity to positive infinity, and the derivative tells us what f is doing. Okay, we had two critical numbers on it. So we had a critical number at -1, and we had a critical number at 2. That's where the derivative was 0, okay, in this case. Okay, to the left of it, it was negative, so that means the function was decreasing. And then in between -1 and 2 was also negative, so it's still decreasing. And then beyond 2, it was positive, so that means it's increasing. So if you actually had to sketch what this graph looks like, it would be what f looks like anyway. It's going to be decreasing, 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 hits -1, flatlines a bit, and then decreases again, and then hits positive 2, and then it increases again. So you can see that the only extrema is right there. It's a relative min. This is neither because it doesn't actually make a hill or a valley. It's just flat lines for a second and then keeps going down. Okay, so this blue is supposed to represent a sketch of f. We don't actually know what it looks like, but we know how it behaves. So that's basically what I drew in there. Okay, could be helpful to do that. Okay, example problem number 3. Let g be the function given by this function right there. X to the 4th minus 4/3 x to the 3rd. What is the value of x on that closed interval where it has an absolute max? Okay, so because it's a closed interval, we are going to want to test those endpoints. So we are going to have to test g of -1 and g of 1. Okay, first thing we're going to do is find the critical number. So anytime you see maximum, think first derivative. So I'm going to do the derivative right here. A light bulb should be going off in your head every single time you see that. Here's the derivative right there, just using some power rule. To find critical numbers, you have to set this equal to 0 or undefined. But this is a polynomial, so it's defined everywhere. We don't need to worry about the or undefined part, but do not forget about that because a lot of times you are going to need that. We need to solve this using some old-fashioned algebra. I'm going to factor out a 4x squared, and you have x minus 1 here is equal to 0. The critical numbers then are going to be where this is equal to 0, so that's just 0, and where this is equal to 0, so 1. So we have two critical numbers, 0 and 1, and we're going to make a critical number line. And it goes from -1 to 1. So 1 is a critical number but, because the derivative is 0 there, but really it's an endpoint, so the derivative is actually not defined at an endpoint because there is no other side to the derivative. You don't really need to know that for this problem, but just throwing that out there. And then there's 0 on the critical number line. We're looking for not f, but g prime is telling us what g is doing. Okay, test the number in between -1 and 0. We're going to throw that into the derivative. Remember, the derivative tells us what the original is doing. Do not plug the number between -1 and 0 into the original. That's just going to tell us the y value. It's not going to actually tell us what the original is doing. The derivative tells us what the original is doing, so plug it into the derivative. If you plug in, I don't know, a good value might be -1/2 into that 4x to the 3rd minus 4x squared, the 1/2 is going to be smaller here than here because it's 1/2 to the third power, which is going to make it smaller. But an easier way to do it is actually just look at this right here. Okay, it's already factored, so it's easy to try to figure out the signs of everything there. So what we're going to do is I'm going to plug in 1/2 to this 4x squared part right here. Well, that's positive. And then you put 1/2 in here. Well, that's negative. Positive times a negative is going to be a negative here. So that means G is decreasing here. Okay. Do the same thing only with maybe positive 1/2 because we want something that's in between 0 and 1 here. So you're going to have a positive, and then 1/2 minus 1 is also going to be negative. So then you're going to have decreasing there as well. And we're looking for the absolute max. There's no relative max here, so we don't really need to worry about that, but we do need to test the endpoints. So that's what we're going to do. We're going to test G of -1 and G of 1. Okay, we want to find the absolute max of G. That means we need the Y value for this. So we need to plug in -1 into the G equation, not G prime, but the actual G equation. So you're going to get 1 minus, well, actually, we're looking for the X value here. What value of X? So minus 4/3. Actually, it's going to be plus 4/3 on that. So you'll get 7/3 for that one. Okay. We're going to do the same thing with just regular old 1, which is going to be 1 minus 4/3. So it's going to be 3/3 minus 4/3, which is -1/3. So you should be able to see that this is going to have the bigger Y value, but it's asking for what X value. So that's super important to understand. So the answer for this one is going to be -1 because that's the X value. Now, for fun, if you wanted, you didn't even have to make that number line. Okay, if you just wanted to actually plug in that G of 0 right away, you would have gotten 0, and you would see that it's also not going to be the absolute max. But we also saw it wasn't a relative max, so there's no way it could have been the absolute max either. It's only decreasing after -1, so that's another way you could actually look at this, is it's only decreasing after -1, so that the max would have to be at -1 because after that the Y value is only going further down. So there's multiple ways of doing this. Whichever way works for you. I basically just showed 3 different ways, just testing that critical number. You can make the critical number line, or you can just kind of look at it conceptually and think, okay, well, it's -1, and then it's decreasing after that, so it can only max out at where that -1 value is. Either way, you're going to get the same answer, whichever technique you do. If you want, you can use a combination of them as well. All right, next section is all about concavity and inflection points, and the standards are: a function's derivative can be used to understand some behaviors of the functions, same enduring understanding as the last section. The learning objectives is, this time, you need to be able to justify conclusions of the function based on its derivatives. In this case, it's the second derivative. The standards: the graph of a function is concave up or concave down, so concave up or down on the open interval if its derivative is increasing or decreasing. So if the derivative is increasing or decreasing, you can look at it that way. An easier way, in my opinion, though, would be just to be looking at the second derivative of the function, and that basically tells you if the second derivative is positive or negative. It tells you whether it's concave upward or downward. Okay, we're going to talk about that in more detail, a little bit more mathematically, but again, just preloading your brains. The second derivative may be used to locate points of inflection as well. It's going to actually be similar to finding extrema, so hopefully you understand that as we go over it. Okay, second derivative and concavity. Okay, if the second derivative is positive, then it's concave up. Okay, so what I want you to do, notice here on this graph of f, it's bending up here. And as it's bending up there, the second derivative is positive. It's above the x-axis. However, when the second derivative is negative, if it's less than 0, notice it's less than 0 right here, it's concave down. Okay, they're concave downwards, as it says right here. So the second derivative tells you if it's concave up or concave down. Now, if the second derivative is 0, then it's linear, which means it doesn't bend at all. It's not bending up or bending down because it's not bending at all, so then it's just equal to 0. Okay, so that's the number one thing that you need to understand. If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. It has nothing to do with increasing or decreasing. As you can see from the graph, it's increasing and decreasing that green section. Okay, it just means it's concave down, but it has nothing to do with increasing, decreasing. Again, that's the first derivative. Make sure you don't get those two confused. Now, it does make sense if you think about it conceptually. If the second derivative is positive, that means its derivative is increasing. If its derivative is increasing, it should be increasing at a faster rate. So if you notice this part right here, so I'm in purple now, this is going up and it's increasing at a faster and faster rate as it's going up. Okay, it's not just going up linearly, it's increasing faster and faster. Same thing if you go the other way, only the opposite. So that's another way of thinking about it with concave up and concave down. But the easiest way is just kind of what I have outlined already. Okay, the second derivative in concavity, you can notice right here that this is this purple is quadratic, so this one on the left here, the derivative, or the second derivative of anything that's quadratic is just a constant. And if you notice, this constant is positive because a quadratic is always concave up. Okay, so its second derivative is always going to be positive. Now this also makes sense from a if you actually worked it out. So say you had f of x is equal to, I'm just going to use a very simple quadratic, x squared. Its first derivative is 2x. Its second derivative is just going to be 2. If you notice, 2 is greater than 0. So that means that this is concave up. Well, every quadratic that's pointed upward is going to be concave up. That makes sense. Now, if I did negative x squared, then it would be negative 2x and negative 2, so it would be concave down, which makes sense because negative x squared is concave down. But I just kind of wanted to show you a really quick example. Okay, this one on the right now, if you notice, this is the original right here. The red is the second derivative for both of these right here. But if you notice this part right here, it's bending up. And if you notice where it's bending up, that second derivative, which is in the red here, is positive. Okay, but if you notice, there's a cusp there. Okay, there's a cusp right there. So the derivative doesn't actually exist there. So if you notice, it just ends up being an asymptote. And the other side of it, it's concave up as well. And if you notice, that derivative, or that second derivative, is also positive throughout. So it's actually concave up both sides on this graph on the right. It might not look like it, but it is actually bending up here, and it's also bending up here. Okay, inflection points. So inflection points, or sometimes it's called points of inflection. It happens when the inflection, it happens where the concavity changes, or another way of looking at it is where the second derivative changes sign from positive to negative or negative to positive. So it's similar to extrema, whether you have relative max or relative extrema, I should say, relative max or relative min, only in this case, there is no relative min and max version of inflection points. It's either just an inflection point or it's not. Okay, in this case, it's concave down and then it's concave up. So that second derivative is 0 right here where it changes from concave up to concave down. So this is actually the second derivative right here, and then this is the actual function. Okay, the opposite would be true if the graph looked like this. Okay, the inflection point is, I don't know, somewhere right here. There, the second derivative is going to be equal to 0. So if, say, the graph was like this, the second derivative for this one, let's color code this as red. The second derivative would be like something like this. And it looks like that. And again, it's where the inflection point changes. It does not need to be at the origin like I have right there. It just so happens that's the way I drew it. But hopefully you see through the examples we do, this will make more sense. All right, example problem number 1. The second derivative of the function g is given by g double prime of that. So that the second derivative is already given. We don't actually have to find it by doing any power rule or anything like that. It's just already given. Okay, what value of x on this interval right here does the graph of g have a point of inflection where the concavity on the graph changes from concave up to concave down? So in order to do this, we're actually going to need to graph this out. Okay, there's no way to actually solve this by hand, so we're going to need to throw this in a calculator to basically figure out this answer. So that's what we're going to do right now. All right, so here is a graph of that second derivative right there, and you'll notice that there's a second derivative equal to 0 there, and there. Okay, but the problem is specifically asking, where does it go from concave up to concave down? So that means this second derivative would have to be from positive to negative. Okay, this first one right here at negative 2.3, it goes from negative to positive, so that means it would go from concave down to concave up, but we want the opposite, so that's not going to work. This one goes from positive to positive, because it doesn't actually cross the x-axis there, so it's positive to positive, so it's concave up to concave up. It's not actually an inflection point. This one, however, goes from positive to negative, so this one would actually be the inflection point that changes from concave up to concave down. So 1.1 is one of the answers, and then the other one over here goes from negative to positive, but again, that would be concave down to concave up, not the one that we want, which is concave up to concave down. So the answer for this one would just be that 1.1 value right there. So that means the answer for this would be A. Okay. It is important to note that you cannot solve this without the graph. Okay, so it's not cheating to use your calculator because you wouldn't be able to do this any other way. Okay, example problem number 2. The first derivative of a function is given by that, and then it says where is h concave down? So h prime is this, where is h concave down. So it is important to understand that we need the second derivative, but the first derivative is already given. So what we need to do is the derivative of this. Sometimes you're given the original and you have to find the first derivative and then take the derivative of that to find the second derivative. This one starts at h prime, so what we're going to do is do the derivative of this real quick using power rule. So you should have 4x to the third minus 3x squared plus 1. Okay. Now to find the inflection point, we need to set this second derivative equal to 0 or undefined. It's a polynomial. It's defined everywhere. There's no division by 0 or square roots of a negative or anything like that. So what we're just going to do is solve this right here. But the problem with this is going to be really hard to solve algebraically. In fact, it's impossible. So what we're going to do is we're actually going to graph this. We're actually just going to graph this part right here and figure out where it's equal to 0, and then use that to figure out where the second derivative is negative, because where the second derivative is negative, that's where h is concave down. So let's go back to the calculator real quick. It is important to note you don't have to actually use Desmos for this. I just keep using this because it's on my iPad. I just keep using this because it's easier to record a video on, but you can use your TI-84 to do the exact same thing. So I'm going to graph that second derivative really quick. So it's going to be 4x to the third minus 3x squared plus 1. Now you cannot actually solve this equal to 0, so without using a calculator this would be really hard to find. So here's that value right there. Rounding to 3 decimal places, it looks like it's negative 4.055, and we're looking for where it's concave down. Okay, so where it's negative. So let me zoom out really quick on this. So it looks like the second derivative is equal to 0 right there at negative 4.55, and it's negative anywhere before that negative 4.55. So that means it's basically negative. The second derivative is negative from negative infinity to that negative 4.55. So if we go back to the original problem, that means that the answer would have to be D, negative infinity to negative 4.55. Again, basically all I did was figure out for concave down, that means the second derivative has to be less than 0, so it has to be negative. I graphed the second derivative and figured out where it's negative. It's from negative infinity to negative 4.55, so that's how I found that answer. All right, so example problem number 3, it says at what x values, so we're looking for x values here, does the graph, okay, this whole thing right there have a point of inflection. So first thing we're going to need to do is find the second derivative. So first thing is, let's find that derivative. So you should have negative e to the negative x plus, okay, we got to do product rule here because it's two functions multiplied by each other. So it's going to be f prime g plus g prime times f. Okay, plus, do the same thing with this part right here, the x squared e to the negative x. So it's going to be f prime g plus g prime f. Okay, I'm going to simplify this because it's pretty ugly just the way it's looking right now. Okay, it looks like this and this can combine. So then you just have e to the negative x on that. Okay, this one and this one are just going to straight up cancel each other, which makes it pretty nice. Minus e to the negative x times x squared. Okay, that's the first derivative, but we need the second derivative for points of inflection. So every single time you see it's a point of inflection or concavity or anything like that, a light bulb should be going off in your head. I'm going to need the second derivative. So let's find the second derivative now. Second derivative is the derivative of the first derivative. So you're going to have negative e to the negative x minus, now we have to do the derivative of this whole thing right here. I'm going to do that in parentheses just so I can distribute that negative later. So it's going to be f prime g plus g prime f. And since it's the second derivative, we're going to need to set that equal to 0 or undefined, but it's defined everywhere because there's no division by 0, so we don't need to worry about the undefined. But we're setting it equal to 0, and we're going to have to solve this, which is kind of crazy because it's all over the place. But first thing I'm going to do is distribute that negative and then factor out an e to the negative x. So it's going to be negative e to the negative x plus x squared e to the negative x minus 2x e to the negative x is equal to 0. All right, I'm going to factor out a e to the negative x here, and you're going to end up with negative 1 plus x squared minus 2x is equal to 0. So what we need to do now in order to solve this equal to 0 is we need to set each factor equal to 0. But we don't need to worry about that e to the negative x because that is never going to be equal to 0. It's exponential. It is literally impossible to set that equal to 0. So we just need to worry about that quadratic piece, setting that equal to 0 and solving. So that's what I'm going to do. X squared minus 2x minus 1, setting that equal to 0. All right, to solve this, I'm going to use quadratic formula. So then you're going to end up with x is equal to negative b, so that's just going to be 2, plus or minus the square root of b squared minus 4ac, so 4 times 1 times negative 1, all over 2a, so it's just all divided by 2. All right, this simplifies like that. And you end up with 2 plus or minus the square root of 8 over 2. Okay, well, that simplifies because the square root of 8 has a perfect square in there. I'm going to write that over here. So it's going to be 2 plus or minus 2 root 2 over 2. Divide everything by 2, you get 1 plus or minus root 2, which the answer for that one is going to be D, because it's got 1 plus root 2 and 1 minus root 2. Now, it's multiple choice, so it makes it a little bit easy to know that it's, that's the answer. But in actuality, you are going to want to, test this interval to make sure that the concavity actually does change, similar to how we did that with the first derivative. So what I'm going to do is I'm going to erase this top part here just so we have some room. All right, so if this was a free response problem, you would need to test this out. So what we're going to do is make a number line. And on the number line, we're going to have 1 plus, should say 1 minus root 2 and 1 plus root 2. And the second derivative is going to tell us what the y is doing, and we need to test those intervals to figure out what is going on in between so we can figure out is the second derivative changing sign. If it is, then it is a point of inflection. All right, so to figure out the second derivative to the left of this value right here, I'm just going to plug in negative infinity into that second derivative. So if I plug in negative infinity on this, you're going to have, well, plugging negative infinity here is going to be infinity, and then the biggest value of x right here is going to be infinity as well. So that's just going to be infinity times infinity. That's positive infinity, so that means it's going to be concave up right here. In between 1 minus root 2 and 1 plus root 2 is 0. So I'm going to plug a 0 in to that second derivative, this whole thing right here. Just plug in 0 on that, and you're going to get 1 times negative 1, which is a negative. So that's concave down. So right there, that one definitely is an inflection point because it went from concave up to concave down. All right, so now I'm going to plug in a value that's to the right of 1 plus root 2. A good value is probably, 3, I guess would be a good value to do. So you plug 3 in there. This is going to be positive. That's going to be 9 minus 6 minus 1. That's still going to be positive. So that means it is still concave up right there, and it changes from concave up to concave down to concave up. So D is the answer. But again, the multiple choice kind of gives that away because it helped us out, but if this was a free response, you would need to test the intervals like I did right there, so make sure you understand how to do that. It's similar to what we did with the first derivative with the increasing, decreasing, only this time the second derivative is telling us what the original is doing in regards to its concavity, if it's concave up or concave down. All right. Onward we go. All right, this next section is going to be all about mean value theorem. Here's the standards. It's the same enduring understanding as some of the other ones. Existence theorems allow us to draw conclusions about a function's behavior on an interval without precisely locating that behavior. Okay, and then it says learning objectives justify the conclusions about functions by applying the mean value theorem over an interval. So that's what we're going to be able to do. Certain conclusions, does mean value theorem apply? If so, at what point does it apply? That sort of thing is what we're going to be doing in this section. It'll make more sense once you understand what mean value theorem is. The essential knowledge that you're going to need for this section is stated right here. If a function is continuous, okay, so it has to be continuous on this closed interval and differentiable over that same interval, only it's an open interval, then mean value theorem guarantees, that means there has to be, no matter what, a point within that open interval from A to B where the instantaneous rate of change equals the average rate of change over that interval. Okay, so basically the instantaneous rate of change, the I rock, is equal to the A rock. But that's only if if it's continuous on that closed interval and differentiable on that open interval. Okay, as long as it's continuous and differentiable based on those intervals right there, that means there has to be a point where this is true. Okay, now that is a lot to wrap your head around. If you're drawing a picture in your head of this and you understand this just by me talking about it, that is really amazing. If not, I'm basically going to break this down using examples, drawing this out so it makes more sense. Okay, here's a graph right here. Clearly you can see that this is continuous on that interval and differentiable on the interval, the open interval, continuous on the closed interval. From here, there's no holes, jumps, or gaps. There's no sharp turns. Okay, it's continuous everywhere, it's differentiable everywhere, except for the endpoints. It can't be differentiable at an endpoint because the derivative has to exist on both sides. It has to agree on both sides. In this case, it doesn't, but that's why it's the open interval for those. Anyway, what mean value theorem states is that the average rate of change, so we have one endpoint right here and one endpoint right here, and if you took the slope from one endpoint, let's just say this is A and this is B over here, the slope of that right here, it's basically saying that there has to be another derivative at a point that has the exact same slope as this. Okay, I don't know what the slope of it is here. I can figure this out because the numbers are given, but that's not important. What is important is to understand that there is going to be at least one point that has the same slope as those endpoints because it's continuous on that closed interval and differentiable on the open interval. Now, what does that mean? Here we go. So we have that same graph again from A to B. Here's A, and here's B right here. And there's a certain slope in green there. Okay, this is the average rate of change, whatever the slope of that green is. Now, if you notice, this is an instantaneous rate of change because it happens at one point, and it's equal to, it has the same slope as that green. Okay, so it has the same slope, it's parallel. You can also look at it right here. Okay, I only threw one of those in there, but this one also has the same slope, and that's an instantaneous rate of change because it's based on just this one point that it's grazing right there. That's what mean value theorem states. If it's continuous and differentiable, there has to be a point that has the same slope as the slope of the endpoints, at least one point. In this case, there's two. There could be way more than two. Okay, at minimum, there has to be one, though. So there has to be at least one. That's what it's basically saying. So if you connected the dots from one endpoint A to B on the graph, there's a certain slope there, okay? There has to be at least one point or multiple points, or could be multiple points, that has the same slope as the slope of those endpoints. That's what mean value theorem is stating, okay? Here is it written out more formally. If it's continuous and differentiable on those intervals here, there has to be at least one point. There exists a point. It could be more points, but at minimum there's one point such that the derivative at that point is equal to the slope of the endpoint. So A and B are the endpoints. C is where that slope is actually occurring, and then we have that graph there. Again, there is multiple because you could have one there. Okay, so there is at least one point C on the open interval A to B where the tangent line is parallel to the segment with the endpoints from A to B. That's what it's basically saying. It's the same kind of picture right here of what I was just talking about. Okay, so we have the endpoints here and here, and the slopes are all parallel to the slope of those endpoints. If a function is continuous on the closed interval from A to B and differentiable on the open interval A to B, there exists at least one number C in which this is true. Again, I'm basically just repeating myself over and over again, but it is really important that you understand this concept. Now it says, what could happen if the function is continuous but not differentiable? If we relax the hypothesis of a theorem, the conclusion could still be true, but it doesn't have to be true. That's the main thing that this is talking about here. So what I'm going to do is actually draw an example of what this is talking about. Okay, so the function is continuous from A to B. So here's A and here's B. It's going to be continuous but not differentiable. So I'm just going to draw something like, I don't know, like this. And there's a sharp turn. So it's not differentiable from A to B. Okay, even though it is continuous from A to B. However, if you notice the slope of the endpoints, I'm going to use a different color here to show this. The slope of the endpoints here, there is other points like here and here that has the same slope. Okay, so it could be true with it, but I could also make one that just has a straight line here and then a straight line here. Okay, now if you notice the slope of the endpoints right here, there is not a point that has the same slope as that. because it's a sharp turn. It says it's not differentiable on A to B. So you can't just do, oh, there, it's parallel, because it's not actually differentiable at that sharp turn because the derivative doesn't agree on both sides. I mean, you could draw a tangent line anywhere on this for any slope. Since there's not just one, you're just going to say it's not differentiable. So it doesn't always happen if you do it that way. So if you notice, this one does work, it just so happens to work, but it doesn't have to if it's not differentiable. Here's a function that is continuous but fails to be differentiable at a single point. So it's not differentiable here. Okay. Now the slope of the endpoints clearly is 0. Okay, it looks pretty clear to me that it's actually 0. But if you notice, there is no point that it actually has a slope equal to 0 anywhere. Because, again, this is not differentiable here. You can't make a tangent line here, because if anything, you could do it infinitely many places on that. So it's not differentiable there. Mean value theorem would not apply on this. How about a function that is differentiable from A to B but fails to be continuous? Well, it says, is that even possible? The answer is no, it's not possible. Okay, you can't be differentiable if you're not even continuous. Okay, so for example, let's just make a non-continuous graph here. So I say I do this here, and then I do something like that. Okay, clearly it's not differentiable there because there's a jump in there. Okay, even if the derivative exists on both sides and agrees on both sides, there's still a jump there that's going to throw off that limit definition of derivative, so it's not actually differentiable there. This was all covered in the last unit. If you're differentiable, you're automatically continuous. You cannot be differentiable and not continuous. That does not make any sense. Okay, graph a function that is continuous from A to B but fails to be differentiable, yet despite this, there is such a point where this is true. Well, I actually already did that. I did that right here. Okay. It's continuous, but it's not differentiable, but there is still a point that matches the slope of the endpoints. Okay, and that's perfectly legal. But mean value theorem states that if it's continuous and differentiable based on those intervals, the closed interval of A to B for continuous and differentiable, the open interval from A to B, there has to be at least one point. It's impossible to break that rule. If you do break the rule, though, definitely let me know because we're going to be famous because you just basically broke a theorem that was invented, 400 years ago. When the hypothesis of a theorem is true, the conclusion must also be true. When the hypothesis is false, the conclusion could be true or false, again, depending on it. Okay, the mean value theorem is tested regularly on the AP exam and in this class, particularly in problems with the functions presented graphically or with a table of values. It is important to understand that. So you have to understand this theorem forwards and backwards because sometimes you have to use it in a not so direct way. Sometimes it doesn't even use the word mean value theorem and you still have to solve it using mean value theorem. So it's not always clear. We're going to do a bunch of examples so this makes sense. Here is an XKCD comic that I thought was pretty funny. It says Rawls theorem. Okay, Rawls theorem is basically mean value theorem, only this time the slope, the instantaneous rate of change, is equal to 0. Okay, you can see it says it right here, actually. All right, so the slope of the endpoints from here to here is actually equal to 0. So it's basically saying if the slope of the endpoints is equal to 0, there has to be at least one point where the slope is equal to 0. Okay, so it's just mean value theorem, only in this case the derivative is equal to 0. Okay, it says, Rawls theorem states, blah, 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 what I just said. What's funny is this little comment at the bottom. It says, every now and then I feel like the math equivalent of the clueless art museum visitor squinting at a painting and saying, come on, my kid could make that. Because this is so basic. Like if you think about it, if you started at 0 and ended at 0, your average rate of change is 0. That means at least somewhere along the lines you had to be 0 again. It just seems very obvious. Okay, because if you go somewhere and you end up going where you started, you had to at least be stopped somewhere in between. Okay, so you end up where you started. Here is the place where it's also equal to 0. You can even do it upside down if you want, or have multiple places. The slope of the endpoints is 0, 0 here, 0 here, 0 here. Okay, and again, it's based on if the graph is continuous and differentiable on those intervals. Here's a real-world analogy that I like to use. Okay, Vicky lives 150 miles from the beach. Okay. So that's point A to point beach. And I'm going to connect the dots here. Okay. She leaves her home at noon and arrives at the beach at 3 p.m. So it took her 3 hours. So it's 150 miles in 3 hours. Okay. The average rate of change of her distance is 50 miles per hour. Okay. I just did this divided by 3, 50 miles per hour. On average, they were going 50 miles an hour. Okay. Now, that means that along this trip, that there had to be at least one instance where Vicky was driving 50 miles an hour. Okay, if they were going under 50 miles an hour the entire time, their average would not be 50 miles an hour. They might have gone 100 for a little bit, but they still had to get to 100, so that means they hit 50 at some point. Okay, they had to at least have gone 50 at some point throughout. So that means the average rate of change at some point is equal to the instantaneous rate of change. So she was driving while she was looking at the speedometer. It had to have reached 50 at least once. If it never went to 50, say it was always 49 and it never went to 50, her average would never have been 50 to begin with, because again, it never averaged out to that. So that's basically what mean value theorem states. The average of the entire trip is equal to, there has to be at least one instance where the trip they were going that fast, unless they teleported or something silly like that, but then that would not be continuous for that. But that's a whole other story. All right, example problem number 1. It says let f of x equal 4. It says let f of x equal x to the 4th minus 2x squared. Find all the values of c that are guaranteed by mean value theorem. Okay, and it has to be on this interval. So first thing that we're going to do is we're going to find the derivative. Okay, there's no second derivatives in this mean value theorem stuff. So we're just going to find that first derivative. And we got something like that. Okay. Now this needs to be equal somewhere between -2 and 2, whatever the average rate of change is. So what we need to do is figure out that average rate of change. So this is going to be equal to f of 2 minus f of -2. So that's change in y over change in x. So if I plug in 2 for this right here, you're going to get 16 minus 8. So you're going to get 8 minus 8. Okay, that's kind of lame. Divided by 4, which is just going to be 0. So you basically need to just set this equal to 0 and solve to figure out that value. So let's do that. Okay, so we're going to factor out the 4x here, and you're going to get x squared minus 1 is equal to 0. Okay, we're going to solve this. You're going to end up having x is equal to 0 and plus or minus 1. Okay, all of those numbers are in the interval. So it says find all values of c. Those are all the values of c right there, in which the average rate of change is equal to the derivative. That's the first part. The next, it says explain why mean value theorem does not apply for this one right here. Okay, for every point on the interval. Okay, so the reason why it would not apply on this is because this 1 over x is not continuous at x equals 0, and x equals 0 is in that interval. So the answer is because it's not continuous. It's also not differentiable on that interval as well. Okay. The next one, it says determine whether mean value theorem can be applied to f on the closed interval from a to b. If it can be applied, find all the values of c that guarantee mean value theorem. If mean value theorem cannot be applied, explain why not. Okay, well, it definitely can be applied for both of these because they are both continuous and differentiable. Okay, they're both polynomials. So that means you could take the derivative of them. There's no division by 0. There's no continuity issues that we have to worry about. So this is going to work for these two. But now it says find those values. Okay, so part A, what we're going to do is take the derivative and set that equal to the slope of the endpoint. So if I plug a 3 in there, I'm going to get -9 plus 9 is 0. Plug 0 in there, it's 0. Divided by 3. 0 divided by 3 is 0. Okay, so now we're just going to solve this, and you're going to get x is equal to 3 halves. Now 3 halves is between 0 and 3, so that ends up working out as the answer for part A. For part B, we're going to do the same thing. We're going to do the derivative. We're going to set it equal to the slope of the endpoint. So f of 2, if you plug a 2 in there, you're going to get 4 minus 10 is -6 plus 4 is -2. Minus, plug in 0, you're going to get 4 divided by 2 minus 0, which is just 2. Okay, simplify this out, you're going to get -3. Add 5 on both sides, you're going to get 2x is equal to 2, and you're going to end up with x is equal to 1. Okay, x is between 0 and 2. That's actually directly between it. So you know it fits on the interval, and that ends up being our answer for that one. And those basically all those problems there. Okay, onward we go. All right, so for this one, it says the function f is continuous. It doesn't say it's differentiable, though, so that's important. From -2 to 2, the slope of the endpoints, it looks like it's going to be 0 because they're both at 0. Okay, I'm going to graph that out so it makes more sense. It says there's no c where the derivative is actually equal to 0, which is weird because the endpoint slope is equal to 0. Okay, so which of the following must be true? All right, so first of all, I'm going to graph some dummy graph of what this is. So it's -2 to 2, and they're both equal to 0. So this is equal to 0 here, this is equal to 0 here, and there's no point where the derivative is equal to 0. So I'm just going to make a graph that just has sharp turns and just looks like that. Again, it's just a dummy graph to kind of give us an idea. And we're looking for things that disprove any of the answer choices, A, B, C, D, or E. If it disproves it just once, it's not true. It doesn't have to be true. And again, it's based on what we wrote here. It says must be true. So A right here, it says the derivative is always positive, which means f is always increasing. Well, our dummy graph shows that it's increasing and decreasing, so it definitely cannot be A. Okay, it also can't be B as well because it's saying the derivative is negative, which means f is decreasing. But again, I have increasing and decreasing on my dummy graph, so it's automatically going to throw B out. C, it says the derivative exists. Nope, because the derivative does not exist here, here, and here because of those sharp turns. So it's definitely not going to be that one. Again, it says must be true. So if I can come up with one example where it's not true, it's not an answer choice anymore. D, from -2 to 2, the derivative exists but is not continuous. If the derivative exists, the derivative has to be continuous, so that doesn't make any sense. Well, this leaves E as our only answer. For some K, the derivative does not exist, which is true because, again, it doesn't exist here, here, or here. And that's the only way to do it, where the derivative is not equal to 0 anywhere. Okay. Some people might go, what if you just drew a straight line between those two graphs? Okay, well, that means the derivative is equal to 0. So you're actually breaking one of the rules of the problem. It says the derivative, there's no point where the derivative is equal to 0. So you cannot just draw a straight line. That would not work either. All right, let's go to the next one. All right, example problem number 3, the function f is continuous and differentiable from 0 to 4. The table above gives selected values of f. Which of the following must be true? Okay, again, if you can come up with one example to break it, it's not going to be true. All right, when in doubt, graph it out. So that's actually what I'm going to do here. So it's going to be a crazy thing to graph because there's a lot of points here. So 0, 2, 3, 4. So it's just going to be 2, 3, and 4. I'm not going to draw this to scale because it doesn't really need to be. So 1, 2, 3, 4. 1, 2, 3, 4. All right. And 0, 2. 1, 3. 2, 4. 3, 3. 4, 2. All right. That's a cool looking graph. All right, it's continuous and differentiable. So I'm just going to draw a nice little smooth curve here. Something like that. It doesn't really matter. If you notice, I added some squiggles in between. Sometimes that helps, so that's why I did that. And then just say which of the following must be true based off that dummy graph. Okay. Now you could augment the dummy graph too, so don't just think you're married to whatever graph you make. You can do whatever you want for this. In fact, I probably should have made it go negative a little bit first because sometimes there's answers with the negative. But again, it doesn't really matter. All right, it says the minimum value is 2. Okay, the answer for that one is definitely false because of that new dummy graph I wrote in orange. The minimum value could be smaller than that. Okay, just because of those given values are selected there, it doesn't mean that there's values that aren't smaller than it. So there could be values smaller than 4. The max value, again, could be greater than 4, as you can see right here. I made it greater than 4, so that's definitely not going to be true. C, f is greater than 0 from 0 to 4. Nope, I have some negatives here and here and here. Okay, so that's definitely not going to be the answer. The derivative is negative. That means f is decreasing from 2 to 4. Not necessarily. I have it going up and down in there. So that means E has to be the only answer. It says there exists a point from 0 to 4 where the derivative is equal to 0. That absolutely has to be true because it's continuous and differentiable, and the slope of the endpoints is 0. So that means it has to be 0 at least in one spot here, even if it's negative down here. So E is the answer based on mean value theorem.